Hi everybody, my name's Isaac Grossoff, and I'm going to be telling you about Nudge, a policy which stochastically improves upon first come, first serve. This is joint work with my co-authors Kunha Yang of Tsinghua University and Zeev Scully and Moore Harkle-Walter of CMU. The setting we'll be looking at is MG1 scheduling. What that means is we have a server and a queue, and jobs arrive according to a Poisson process with some arrival rate lambda. The job sizes will be distributed according to some general distribution S, and the sizes will be sampled IID from that distribution. We're going to be looking at the response time distribution T. That's the distribution of time from when jobs arrive at the queue to when they complete at the server. And the question we'll be looking at is, how should we schedule the jobs? Now, as a baseline, let's look at the first come, first served scheduling policy. First come, first serve is a simple, practical policy. It's used all the time in real systems, and it has some good theoretical properties. Here we have a plot where on the vertical axis we have the tail probability, the chance that response time exceeds some threshold little t, and we'll plot this according to a log scale. On the horizontal axis we'll have the threshold little t measured in terms of the mean job size. And the setting we'll use has a job size distribution that's hyper-exponential with squared coefficient of variation 3 and relatively low load of 0.4. Here's what first come, first served's tail probability looks like. In comparison, let's look at some more complicated policies, like shortest remaining processing time, shortest processing time with no preemption, and preemptive last come, first serve. Now, in all these cases, we can observe a trade-off. At low thresholds, over here, the more complicated policies do better. But at high thresholds, first come, first serve is the champion. And we can formalize this fact that first come, first serve does well at large thresholds by saying that first come, first serve is weakly optimal. What that means is that in the limit, as t becomes very large, first come, first serve's response time distribution is distributed as c times e to the negative theta t, where that decay rate theta is the best possible theta for any scheduling policy. And this property of first come, first served's weak optimality holds whenever the job size distribution S is light-tailed. That means exponential distributions, hyper-exponential distributions, phase type, Weibull, all sorts of distributions. So let's look at what this trade-off looks like in a specific example. In the case of first come, first serve, the moment a job arrives, we know what its response time is going to be. It just has to wait for all the jobs in front of it, and then it'll get to run. So first come, first serve, whether the job is large or small, they all have similar response time distributions, and it's all sort of medium response time. In contrast, let's look at SRPT. For small jobs, they have very fast response times. They get to skip ahead of everybody. But large jobs, they keep getting delayed by all of these small jobs, and so their response times can be quite large. So SRPT helps small jobs a lot, and that means it has good response time distribution for small thresholds t. However, it delays large jobs a lot, and that means it has poor response time for larger thresholds t, because those ones are dominated by the large jobs. So, here we have a fundamental question of trade-offs. All previous policies have trade-offs. They're better than first come, first serve for small t, or they're worse than first come, first serve for large t, or they're just worse everywhere. Now the question is that inevitable? Is it impossible to find a policy that's just not a trade-off? Or is it possible to beat first come, first serve everywhere for all thresholds little t? We answer that question for the first time, yes. It is possible to beat first come, first serve everywhere. And we pull it off with a policy called Nudge. So, we introduced this new policy called Nudge. And its tail probability looks like this. it's better than first come, first serve everywhere, a property we call stochastic improvement upon first come, first serve. Now this gap might not look like much, but it's actually quite substantial. That's a 12% improvement. It only looks small because this is a log plot of tail probability. More generally, we prove that the probability that nudge's response time exceeds some threshold little t is smaller than the probability first come, first serve exceeds that threshold for all thresholds t and for all light-tailed job size distributions s. And beyond just this, which is already a big discovery, we also improve that nudge has a better asymptotic tail than first come, first serve. It's not just weakly optimal. Its response time tail asymptotically behaves like c prime times e to the negative theta t. It's that same theta as first come, first serve, but a better leading constant c prime. Now, nudge isn't just the first policy to pull this off. Actually, having a better leading constant was previously conjectured to be impossible by Wehrman and Zwart. They conjectured that first come, first serve had the best possible leading constant, but we managed to improve it with nudge. So, I've shown you that nudge stochastically improves on first come, first serve and has a better asymptotic tail. Let me show you how it works. So, say we have a queue. By default, we'll schedule the jobs in first come, first serve order. But we'll also classify the jobs as either small or large based on their size. Say here's the job size distribution. These jobs might be small, while these jobs might be large. Whenever a small job arrives, if a large job is the last job in the queue, we'll have that small job nudge its way ahead of the large job. So say here's our small job, it'll just nudge its way into the queue ahead of the large job. However, we don't want to overdo it. We don't want to end up like SRPT. So we'll say that large jobs can only be nudged once. If another small job arrives, it has to go to the back of the queue. All right, let me give you some more visceral intuition for how nudge works. Let's say this is what our queue looks like. These humans will be our small jobs, while these giants will be our large jobs. Now, let's say Jack arrives with his cow. He's not doing anything crazy, no magic beans, he's just taking the cow to market. Now, this giant, he'll barely even notice if Jack goes in front of him. So nudge says Jack gets to go ahead of the giant. However, now imagine that Jack's friends start showing up, and they've got their cows as well. Now, the giant starts getting mad just thinking of all these people with their cows going in front of him. We don't want the giant to be upset. We don't want the giant to have a bad response time because that'll ruin our response time tail. So what we say is no one else gets to go ahead of the giant. Just Jack, nobody else. That way the giant stays happy and our response time tail stays better than that of first come, first serve. All right, I've told you how our policy works. Now let me give you some intuition behind the proof. Remember, we want to show that nudge's response time is, in particular, the probability that nudge's response time exceeds some threshold little t is smaller than that of first come, first serve for all thresholds t. Let's focus in on a scenario, just two jobs, where first come, first serve will schedule the jobs with the large in front of the small. Let's say this is a plot of the number of jobs among these two whose response time is greater than some threshold t. And here we'll have all the thresholds. Maybe this is the response times of the two jobs under first come, first serve. And that would lead to this sort of a plot. Now in contrast, say nudge moves up the small job ahead of the large job. The small job will have better response time because it doesn't have to wait behind the large job, while the large job will have worse response time because it has to wait behind the small job. So maybe this is what that plot will look like for nudge. Now on net, here's what the effect of performing the nudge is. Over here, nudge will improve our response time. nudge will improve the number of jobs whose response time is above this threshold, from 2 down to 1. Where over here, nudge will degrade things. It goes up from 0 up to 1. So, the effect of the nudge is an improvement over here and a degradation over here. That's one nudge. Now let's look at one response time threshold, but many nudges. Some nudges will improve things relative to that threshold, while other nudges will degrade things relative to that threshold. What we want to prove is that the rate of these improve events exceeds the rate of degrade events for all thresholds t. Our first key idea is that the rates of improve and degrade events are determined by first come first served's tail and PDF. Now remember, here's what that tail probability looked like from before, and the PDF looks very similar. Our second key idea is that we can bound first come first served's tail and PDF relative to that limiting exponential distribution we talked about earlier. Since this is a log plot, we're bounding it according to this straight line. And while we're using some pre-existing techniques, our bound on the PDF is actually a new result. Now what's important about these bounds is that the lower bound actually ends up telling us that the improve events happen relatively often. And the upper bound ends up telling us that the degrade events happen relatively rarely. And when we combine these, we can actually show that more improve events happen than degrade events as long as we're given the correct, as long as we choose the correct small and large job size cutoffs for our bounds. Now, with that complete, we have completed our proof. Nudge beats first come first serve for every threshold t because of these bounds that hold for every threshold t. Now, let me show you what that improvement looks like in practice. Here's some empirical results. Here we'll have a plot where on the vertical axis we'll show the tail improvement ratio. This is 1 minus the ratio of nudges tail probability to that of first come first serve. And on the horizontal axis, we'll have the threshold in terms of the mean job size. Here we'll look at a higher load of rho equals 0.8. Now, whether we have a uniform job size distribution with relatively low variance, we have an exponential job size distribution with medium variance, or a hyperexponential or bounded Lomax distribution with relatively high variance, the situation stays the same. Nudge improves on first come first serve relative to all thresholds. And that improvement is pretty substantial, something like 5 to 7% throughout almost the entire tail. So this is a big improvement over first come first serve, and it holds consistently. Okay, I've shown you that nudge works. Let me talk you through some future directions for work in areas related to nudge. Now, nudge has one swap per job, at most hard limit. What if we looked at a policy that had 2 or 3 or something swaps per job? Might those policies also achieve stochastic improvement over first come first serve? I will point out that it's important that we have a constant number of swaps per job. If we have unlimited swaps, we're getting into SRPT sort of territory, and that's not good. We know SRPT doesn't improve on first come first serve for all thresholds. Another question is, what range of size cutoffs might work? In the proofs, we had to choose our size cutoffs very carefully. Small jobs had to be very small, while large jobs had to be large but not too large, and a lot of jobs weren't in either category. It would be nice, it would be cleaner, if we could do the same thing but with a single threshold and make all jobs either small or large. And for the empirical plots I gave, that was the kind of nudge policy I was actually performing. So could we prove that a single threshold always suffices. That's an interesting direction. And finally, beyond first come, first serve, what other policies can be improved everywhere? First come, first serve is a very fundamental policy, but there's tons of other policies out there. Can we improve those policies everywhere? Which ones can't be improved everywhere? All right, so in conclusion, I introduced a policy called nudge. It works by giving small jobs just a little nudge in front of the large jobs, but at most one nudge per large job. We don't want to delay them too much. Nudge is the first policy to achieve stochastic improvement over first come, first serve, and it does so for any light-tailed job size distribution. It's also the first policy to achieve a multiplicative asymptotic improvement over first come, first serve, contrary to a previous conjecture. And here's what that improvement looks like in practice. It's consistent throughout the tail across a wide range of distributions, and it's something like 5 or 7%, or even more in some other examples. All right, that's everything. Thank you for watching. I'd be happy to take any questions either in the session or over email. Thanks.